And then we can kickstart. So, hello and welcome everybody. This is the first Oakestra community talk for this particular year. We are glad to have you. Today we have Luca from University of Padova, who's going to be presenting the cool work he has been doing on WebAssembly within Oakestra. But before we go into it, we also wanted to showcase with the community what we have built. So, since this is the first time we're sharing updates, we want to highlight that the second stable release of Oakestra is out now. The code name is Base. And in this release, we bring a lot of new amazing features and stability updates. More specifically, and the coolest of them all is we have a full IPv6 support for all your networking within net managers. We have a very comprehensive command line interface, which you can now use to interact with all of the Orchestra elements and even deploy your applications with, monitor your applications. This is also fully extensible. We have a new element with which we are able to do machine learning to a certain to a very comprehensive degree. We call it FLOps because this is using federated learning elements, specifically integrating Flower components into Oakestra. So this also brings Oakestra into the intelligence world. And then we also have now a functionality for defining add-ons. So if you want to extend Oakestra core components, that you can do with much simpler ease. You don't have to tinker much with the internal Oakestra components. You can just define your own component and make it as an add-on and make it work with Oakestra. And then we have a very comprehensive documentation that we have also released. So if you just go to orchestra.io and visit docs, then you will see that suddenly there's a flood of information that you can read through to see what is going on behind the scenes. So we highly recommend you to do that. We also wanted to remind again that this particular talk is going to be recorded. So again, if you don't want to be seen, then please turn off your cameras and just use the chat. Otherwise, we would love to see you interact with the Oakestra developers who are also here. If you're working on similar topics or you want to showcase your work that you're doing within Oakestra, we want to have these community talks almost once every month or so, as of now, what we are thinking about. If you have something that you want to present, please reach out to admin@orchestra.io, or you can just join our Discord server, where you can also engage with the developers and we can have a more thorough discussion as well. With that, let's get to the sparkling topic why we are here. So Luca is going to be presenting his work that he's been doing on WebAssembly module. To give a very short introduction, Luca is an MSc student at University of Padua, and this work that he's going to be presenting is part of his MSc thesis there as well.
Okay, thank you so much. Okay, so I was saying that this presentation is the same that I'm going to use for my discussion as a master degree thesis. So yeah, it's not customized for Oakestra, but I think it's good enough to show why the motivation behind our work and why we choose the WebAssembly and the Oakestra in particular. Also, I want to point out that in the meeting, there is also Eduardo Tinto, which is a PhD student in our university working on the Edge to Cloud continuum. So yeah, if you have any other question, maybe Eduardo can also answer to in detail to different on the different things that he's working on. Okay, so I start from the context of why we have chosen Oakestra and WebAssembly to as an experiment to test the possibility of this combination. So yeah, everyone knows that we are living in a hyper-connected world where there is a growing interest in exploiting cloud computing and edge computing. And nowadays we are also seeing a lot of computational power increase in edge devices. So devices are getting more and more smart, let's say. And we feel like there is the need of reaching to a hybrid computing model. So some use cases are good to be developed on a cloud computing model. Some others are good to be developed in an edge computing model, but sometimes we might want to have a hybrid computing model, so that can exploit both the benefits of cloud computing and edge computing. So something similar to fog computing, where you can run software in any node of the network, and we refer to this as a computing continuum. So yeah, that's the basic motivations that are behind our experiments. So let's take an application scenario specific tailored to the smart city case and also the automotive case. You know that inside cars we have ECUs that stand for electronic control units, and those are hardware boards that are very, very tailored to the underlying system. So, such as for cars, there are ECUs that controls the brake system, the I don't know, the ADAS system, or the security and safety equipments, and so on. And one key thing to note about this kind of boards is that it is very hard to develop firmware on these boards because the hardware is very different. There are strict requirements in terms of safety and security of the code that you write, and that's also why you get very few updates on ECUs in cars. So let's think about a scenario where we have a smart city that wants to have a cloud infrastructure that can communicate and interact with the ECUs inside the cars going around in the city. So this is a very complex thing to do because we have 100, if not thousands, of electronic boards. They are very, very, they have very constrained power capabilities and also computation capabilities. They are very different from each other, so it is hard to develop one application and think that it is possible to run it on a very different ECU. And think about the possibility of having cars that enters a speed limited zone and have the city infrastructure that can deploy a software module inside the ECU of a specific car entering the speed limited zone in order to be able to interact with the car and set a speed limit such that the user cannot go past that speed limit. This is very interesting to do, and also other use case can be extracted from this specific use, such as having detailed telemetry from the cars going around the city to understand if all the cars are have some problems. So maybe we can avoid to have incidents due to hardware of the car failure. But also we have maybe car crash management, so we can communicate with other cars to slow down in a certain segment of a road due to an accident. Also, we might want to have like traffic forecast. So maybe cars could send the telemetry statistics on a cloudlet, depending of where the car currently is, and then the cloudlet can perform some computation and offload some other computation to the cloud. So this kind of example can be under the name of compute continuum, where there is no fixed computing model, but rather we have a seamless integration of multiple computing architecture. So we might want to be able to run software modules anywhere from the cloud to the network edge. And by anywhere, I mean in intermediate node, in edge devices, in cloud servers, and depending on the capabilities of that specific device and the resources that are accessible from that kind of a device, we can do different data processing, and we can have different level of performances in terms of computation that can lead to intelligence creation as we go towards high performance servers. So to be able to realize a computer continuum vision, we need a common runtime to be able to execute a software components anywhere across the computing devices. And this can be hard because of different challenges. First of all, as I said before, we have heterogeneity of devices and architectures. So running on very resource-constrained boards can be hard because hardware are very different. And also, we might want to deploy virtualization solution and containerization on that kind of boards to be able to avoid, to deal with the heterogeneity, but this implies a lot of overhead. So it might be impossible to run virtual machines or containers on ECUs and electronic boards. Also, we have security concerns because, as I said before, the automotive field is very strict about regulation in how software is built because we don't want to have malicious software running on the cars. And also, some edge devices are battery powered or have unstable power sources. So let's think about all those edge devices running with solar power. And the last point is the main point on why we have chosen Oakestra to help us solving these challenges. And it is because Oakestra is realized on a 3-tier architecture, while existing orchestration frameworks such as Kubernetes are cloud-centered. So it is very hard to have multiple clusters and to have a different hierarchy of cluster to be able to manage the network of devices more effectively. So we have 3 deployment scenarios. Bare metal, so we know on nodes that doesn't have operating system, which are the most resource-constrained board. We have boards that have a real-time operating system, which are very used in the realm of edge devices and also, I don't know, IoT. And in the end, we have also the use case of deploying software on general purpose OS. So think about servers and in data centers. And with my work, I focused most on the last point. So we are thinking about in this presentation, I'm referring to systems that have an operating system. So we want to achieve portability with high performances and low overhead, sandboxing, and then we want to also achieve live migration capabilities, which is the work where Edoardo Tinto is focusing on, to be able to migrate software modules in a stateful and connection-preserving way. So we are interested in this because let's say that our node is going to shutting down soon, but it is currently taking on computation. We want to, instead of stopping the computation, move the software to another node and start it all over. We want to be able to move the computation to another node without having to lose the computation state. Finally, we want to have a flexible orchestration logic and the creation of opportunistic federated cluster. So what is the solution that we propose is to join the benefits of WebAssembly and Oakestra together. And with this, we want to extend the node engine of Oakestra to support an additional runtime, which is wasm time to be able to deploy WebAssembly modules on nodes. So I don't know if you are familiar with WebAssembly, but it is basically a bytecode that was originally created for be able to deploy applications in the web that were written in non-web languages such as C, C++, Rust, and whatever. So instead of having to rebuild those applications in, let's say, JavaScript. With the WebAssembly, it is possible to deploy those applications on browsers directly by compiling the source code of a high-level language to the WebAssembly bytecode. It is highly performant, and there are a number of papers that are comparing the native execution and different WebAssembly runtimes. And also it has sandboxing capabilities, so it is possible to isolate the underlying hardware and operating system from the application running on the WebAssembly runtime. And it is possible also, thanks to WASI, to allow the application running on the WebAssembly runtime to access some of the features of the underlying operating system by having system calls available to it. And so how WebAssembly works? So basically, you can compile any high-level language to WebAssembly bytecode, which is a binary bytecode, and then on the node that you want to run WebAssembly, you have a WebAssembly virtual machine, which is basically a WebAssembly runtime that takes the WebAssembly bytecode and translate it in machine code depending on the target architecture of that specific machine. There is a slide on Oakestra, but I don't think it's appropriate to explain to you what Oakestra is because you know it better than me. But let's talk about our implementation. So it was very, very simple in terms of modification to Oakestra because we have limited the modification to the node engine component of Oakestra. And since the node engine was already built to support different kind of runtimes, such as container and unikernel, it was easy enough to add a new runtime based on wasm-time library to be able to deploy wasm modules on that specific node. So the other component of Oakestra are basically untouched. But I have to also note that we are not fully done with the live migration of WASM modules because with the live migration of WASM module, there will for sure the need to touch also other components of Oakestra to be able to coordinate the migration of WASM module across different kind of nodes. But I think that's a future step in this development process. So one interesting thing that we had to deal about was artifact management. So basically, when you have to run a container on a node, we can, without any problem, just call image registry, a cloud image registry, to pull the image from, and then the node can have all the dependencies and all what it is needed to create the container as the application deployment describes. But there is no such solution for WASM, so there is no a standard like the OCI container standard for WASM modules. So what we did was treating WASM modules as artifact, and then go to cloud artifact registries, such as Google Cloud Artifact Registries, to be able to deploy those artifacts on the nodes in a very, very similar way as we do with container images. So with cloud artifact registries, we have version control, we have a centralized storage for WASM modules that can be reached from the nodes where we want to deploy the WASM modules. And so I think that is a pretty good solution for now, at least while there is no standardized way of managing WASM modules. So we did some benchmarking to be sure that our results aligned with the literature. And we measured how long it takes for WASM to compute some benchmarks. In details, the benchmarks are polybench benchmarking, which are used also in a lot of scientific papers. And so what we discovered was that Oakestra with WASM time implementation is a little bit less performant than running the same benchmark in a container as a native software. And this is because we don't have the possibility of optimizing a specific software for the target architecture, since we don't really know what is the target architecture, because WebAssembly can run on any architecture and any device, and so we cannot make optimization ahead of time. So we have a slight performance degradation, but in terms of how wasn't time implementation on Oakestra run compared to other WASM benchmarks, we do pretty good. We have a slight degradation of performances due to the concurrency logic that we need to run multiple WASM modules at the same time. But I think that is a pretty good result. We have other results. So we have a deployment time benchmark, and we measured how long it takes from when the developer launch the deployment of an application in Oakestra till the application is up and running. And we measured the differences between the deployment time of containers and the deployment time of WASM modules with the same benchmark software on it. And what we discovered was that the deployment time of WASM module is a lot faster than the deployment time of container, because the only step that takes time in WASM is the module compilation to the machine code for the target architecture. And so with this, we can reach a reduction of downtime of application, because we can lower the time that it takes for an application to start. And I think that is also a pretty interesting result to motivate our work. Also, the image size of Docker container can be bigger than the same application compiled to as I was on modules, and this can be good because also we can achieve faster network transfer of images, and we can also have better compatibility with the constrained devices that have lower storage. So also this is a pretty good result that we have. I was able to deploy a set of virtual machines with the Oakestra components and to test out our solution, and everything worked as expected. And the live migration support is under development by Eduardo Tinto with pretty good results. I'm not going to focus in detail on his implementation, because for sure he can explain it better than me. And maybe when Oakestra will have live migration support for WASM modules, he will explain the complete solution to you. But the main key is that each node may want to start an application migration, and the orchestration can collaborate with the node to decide on which node, which is the target node to transfer the migration to. And so, yeah, we might need to make modification to other components of Oakestra to be able to do this kind of collaboration between the node and the other nodes. So before concluding, I want to try to do a little bit of a demo. Hopefully everything will work fine. So let me see if everything is shared. Okay. So, okay, I'm connected remotely on a server at home, so I hope that everything will run fine. So here we have the node engine working. You are seeing the logs of the node engine. Then we have the logs of the cluster orchestrator and of the root orchestrator. I'm sorry, this is the root orchestrator and this is the cluster manager. So I prepared a JSON deployment description, and you can see that we added a virtualization tag, which is WASM. And also, the code doesn't point to a specific Docker container, but instead it points to a Google Cloud Artifact Registry, and specifically the Go benchmark application that I compiled to WASM. So by opening, okay, here is the dashboard. I'm going to log in the API panel of Oakestra. Okay. So I'm going to deploy an application. This is the same code that you have seen here. I'm going to execute it. Okay, so far so good. Now I should be able to see, okay, the application WASM benchmark has been registered to Oakestra, and now I'm going to deploy it. Okay. So right now you should see here that in the logs, the WASM downloader component of my implementation has recognized that the WASM module that I specified in deployment description was already on the host, so it didn't download it again. And it compiled the module to the target architecture. And these are just some benchmarkings of the time that it takes to compile. And it is basically ready to serve. So we see here that the module is running, and also the logging is working because we are seeing the logs of the experiments with the results of how long it takes for the experiments to run. So this was a little demo to show you the implementation. What else? I think that the only thing left was the conclusion. So those are the reasons why we are trying to combine the benefits of WASM with the benefits of Oakestra. And I think there is enough space to start a collaborative effort between our team behind the Compute Continuum project and with you. At least this was like a proof of concept of what can be done with WASM. WASM it's under high development, so features are going out very frequently. So there are some limitations, like there isn't a support right now for networking. So this is a very crucial point. So WASM modules deployed on the node cannot reach the network, but maybe there is a space to work on that. Yeah, so that's it. If you have any question, feel free to ask.
Perfect.
And I hope that this work was interesting for you.
Yeah, thank you so much, Luca. This was a really cool work. So I'll open the floor for any questions. So while we are waiting for questions, I mean, you mentioned, so this was great, first of all. So one question that I have is, this was not clear to me. So the networking components are still not working for the WASM workloads, right? So it is still just a compute.
Yeah, because let's say that the networking feature of a node can be, since WASM works in sandbox, the networking feature must be granted to the WASM module running on that node. So I think that we need to work out how to be able to allow the module to access the networking components that are running on the node. So I'm not sure how we can do that, but yeah.
Okay. Yeah. I mean, because I think that could be very interesting, because then you can cross deploy WASM workloads along with your containerized workloads as well, and then build really like a continuum that you have in mind, right? So pretty cool. Yeah. Okay. Any questions?
A quick question here. Hi, nice work. So, have you tried other engines other than Wasm Time? Like Wasm V8, I don't know.
Okay, so Wasm Time was chosen because on some features, such as the fact that it is written in Rust, which is interesting because we can guarantee some memory safeness, which is crucial in scenarios where we have, like in the automotive or in industrial field, where we need to be sure that the software running on a specific node is 100% safe. Also, Wasm Time in particular offer the Wasm Time runtime as a library to be used from other software components, and also so this allowed us to extend the Wasm Time with the code necessary to compile and run Wasm modules. And this was possible also because we were able to use CGO, since the node engine was written in Go. We used CGO to access the API available from Wasm Time to the node engine. So those are the key features of Wasm Time that we and that's why we choose it to as a runtime for this project. But I think that as there are many Wasm runtimes under development, maybe in the future there will be other runtimes that fill the requirements better. So it's all about experimenting and see what is the best runtime for what we want to achieve.
Okay, thanks.
No problem.
Okay, so I have then one last question if nobody else has a question in mind.
I have one if I
Yeah, go ahead, Bennett. Please go ahead.
Okay, thank you for your talk. On one slide, you had a comparison of, I think it was some compute benchmark, right, of Wasm Time in Docker, just Wasm Time, and native on Docker, right?
Yeah.
And there was still a quite big performance difference with Wasm Time in Docker and outside of Docker. Can you explain a bit why there is so much overhead, or?
Okay, so you're referring to the overhead of Wasm modules deployed with Wasm Time inside a Docker container, and Wasm deployed with Wasm Time as an Oakestra extension, right?
Right, yeah.
Okay. The motivation behind it, I think, is that we need some concurrency logic to be able to run multiple Wasm module in parallel. So if a node has enough resources to run multiple Wasm modules, we need some way to coordinate that parallel workloads. And to be able to do so, we need to coordinate the launch of Wasm modules on the node, and that creates a little bit of overhead in the execution. But maybe there is space for optimization on that. I'm pretty sure that it's there is space to optimize that specific.
So you mean
overhead.
the management? You think there's a management overhead of the deployment, also, but is it still noticeable during execution? I mean, I'm not quite sure what the workload was. It was some compute task, right? But
Yeah,
you
yeah,
measured
yeah.
the time, right? How long the task took. So this also includes the startup time or the...
No. It's only
Okay.
about computation.
Okay.
Yeah.
But still, I'm wondering why this is so noticeable during the computation then.
It is noticeable during computation, but it is the fact is that yeah, we have some degradation in performances that may show that it is preferable to run software in containers. But what happens is that we have other benefits for WASM modules, which are low overhead on most on the resource constrained nodes, and also faster deployment times in terms of deployment time and image size. So while there are some applications that are better to be run on containers, there are some other where some other application that may want to be run on nodes that are not capable of running a container. And so that's where WASM really comes out as a benefit of a run as a good runtimes to be used, because for sure we are not seeing WASM as a replacement for containers, but instead as a way of deploying application that cannot be run in container in the most constrained devices.
Yeah, totally. I totally get that, but I'm still curious why they perform different. But I mean, mostly, I mean, I understand the reason why this is useful to evaluate both, but there are reasons for having both, but I still don't completely understand why they perform so vastly different. But thank you for your. I think that's
no problem.
nothing you
Again,
have
I
to
think
answer because
no problem. I think again it's about the coordination of multiple the logic needed to support concurrency of multiple WASM nodes that maybe lowers the performances, but we can go better in depth into it and see if we can optimize this aspect.
Okay, thank you a lot.
No problem.
We have time for one short question, if anybody still has one to ask. Okay, so then I would like to thank Luca for the great work and also for the presentation. We hope to see more work from your group. I'm looking forward to the live migration works and actually what is happening behind the scenes as well. So I'm keeping my eyes peeled. But thank you everybody for joining. Thank you, Luca, for presenting, and
Thank you.
see you in the next community meeting. Thank you.
Thank you, Luca.